Okay. Our second speaker is Yanhua Sun. She is a PhD student in the lab, and today she'll be talking about LRTS, which is a low-level runtime system abstraction for portability of Charm++.
My talk actually goes exactly opposite direction with British, although we are in the same section. Actually, it's like a British talk go to the topmost level of the charm, and I go to the lowest level of charm. It's like in the civil building. He lives on the 4th floor with a good view of civil, while I'm living in the basement. So the talk is called LRTS, a portable high-performance low-level communication interface. So I'm glad that we have today Korea and IBM people. All of them are the vendors. They provide different supercomputers. Their internet are extremely complicated. In order to utilize their underlying internet, they provide network programming interface. But their programming interface probably only works best for their own hardware. On the other side, we have different programming models. Currently, no single programming model can satisfy every user's need. There are 3 major programming models, including global address space programming model, like the traditional UPC co-array, and now we have the Chapel X10, as mentioned before. For this programming model, it prefers the underlying network to be RDMA support. It's a perfect match for that hardware. For the second category, we have the message passing library. It's specifically, MPI. For MPI, the communication involves both the sender side and the receiver side. And the third category is the message relay or active message model. Charm is one instance of this category. And this is also the focus of my talk. So based on these various hardware and different programming models, the motivation of LRTS is we try to define a minimum set of functions which we can provide to the vendors. And then after the vendor gets this set of functions, they implement on their hardware, then we can run our Charm or other runtime systems. So I'll discuss the goals of LRTS and then talk about the Charm architecture based on LRTS. And I present the core APIs and extended APIs of LRTS. Finally, I discuss some performance of micro benchmarks and the memory performance. I'll discuss about the future work. So based on many years of experience on porting Charm to various supercomputers, we conclude that the LRTS interface should have the goal of completeness, productivity, portability, and performance. So by completeness, I mean the set of LRTS functions should be sufficient to provide to the vendors to run Charm. No Charm features should be lost due to we porting Charm to the LRTS structure. By productivity, we mean traditionally, if we want to port Charm to a new hardware, it requires intensive knowledge of Charm. And with the LRTS design, it should require no knowledge of Charm to port to new hardware. And also for the Charm developers, it should be easier to add new features to Charm without going deeper to the low-level machine layer specifications. And the third is the portability. That means The set of LRTS functions shouldn't depend on any specific machine layers. Instead, it should be common and universal for all the machine layers. However, of course, we know different hardwares have their own space of optimization. So the other side, we still want to maintain the good performance of charm, then we should allow some space for optimization. Keep these goals in mind. Let's go over charm overhead. This figure shows the 5 layers of charm architecture. On the top, we have different applications: molecular dynamics, NAMD, cosmology, Chang'e, open atom, and our new contagion application. Below it is all various libraries and all the special purpose language like British talked about earlier. And in order to support all these libraries and applications, we have charm general programming model. So in charm, the data dependence is expressed in structure dagger. And the problem is divided into chars and char arrays. These arrays hold the data, and the execution of the whole program is triggered by entry method evacuation. Also, the load balancing framework and the performance analysis framework projection also belong to charm programming model level. So below it is the converse runtime system. Converse runtime system is responsible for all the message scheduling and user level thread creation and scheduling. Also, we have the state load balancer that's mainly used for state space search problems like the UTS benchmark. At the bottom of this architecture is all various machine layer implementation. This machine layer implementation directly interacts with the charm converse runtime system and is responsible for communication initialization and do all the message sending and receiving and message queuing. So now with our new LRTS design, we want to abstract all the machine common code into our LRTS implementation, and this LRTS implementation is responsible for the converse initialization or the converse queuing, SMP, non-SMP implementation, and the common collectives implementation. And also we provide a set of functions. So this function needs to be implemented by the lower level machine layers. So after this LRTS design, the machine layer is only responsible for its machine-specific initialization and communication. Corresponding to charm architecture, now we have these charming naming rules. All the functions with the prefix of CK is used for charm programs. CMI functions are used for the converse programs. And now we have the second category of LRTS functions, which we provide to vendors to implement charm on the new hardware. Since LRTS is the bridge of converse runtime and the lower level interconnect, so we need to be clear of charm message flow. In charm, we have two modes called non-SMP and SMP mode. Non-SMP mode is our traditional charm architecture mode. In that mode, we have one process is running every core, and this process is responsible for both computation and communication. And then now with the processors have more and more cores, like 8, 16, or even 64 threads for BlueGenQ machine. We have a SMP mode. In SMP mode, on each physical node, we have one or a few processes. We call these processes as the charm nodes. So within each process, we fire multiple threads. Each thread is assigned to one particular core. And the communication between these threads within the same process are done by passing message pointers. And the work thread is only responsible for computation. And then we dedicate some threads as a communication thread, which are only responsible for the communications, shown like this figure. So when node 0 wants to communicate to node 1, so the messages will go to its communication thread first, and then communication thread is responsible to send this message out, and then holding network to receive new incoming messages. So that's the main functionality of LRTS. So LRTS functions are divided into core APIs and extended APIs. The core APIs are required to implement to run the basic of the charm. And the extended APIs are mainly for performance optimization. The first few functions shows the definition for the startup and shutdown. We define the LRTS init function to initialize the communication network by calling the underlying communication library. Like in MPI layers, we call MPI initialize. And usually we set up all the dynamic communication channels. And PAMI, we also call PAMI init, and doing all kinds of setting up. Also, this function is responsible to get the number of the processes among for the job and get the current number of my process. This information are passed back to converse runtime. At the end of the program, we define the LRTS exit. So it terminates the program correctly, and sometimes it also needs to release the system memory buffers if we use. And the LRTS barrier is mainly to synchronize all the process for the job. Since other function calls in charm are asynchronous, so LRTS barrier is mainly used at the beginning and at the end of the program. So the most important functions in LRTS are point-to-point communication. In order to send a message, we define an interface called LRTS send func. It takes message from converse runtime and sends this message to the dest PE on dest node. Depends on the message size, the underlying network might choose different protocols to send these messages. And one thing we need to notice is that for some hardware, the message cannot be sent immediately. In this case, we need to buffer this message and then try to resend these messages later. So the other function is LRTS advanced communication. So this function is mainly responsible for sending the buffered message, as we said before, and also it needs to holding network to receive message. After this message are received by LRTS, we call handle one received message and deliver this message to the converse runtime system. How we process this message will decided by charm runtime system. So the LRTS layer doesn't have to care about it. So the other set of APIs are extended APIs. The first set is for memory management. As we know, in charm, all the message memory is taken control by the charm runtime system. when you can call CMI alloc or CMI free, and the charm will take care of how we allocate and free these messages. Charm provides a common code to use GNOME alloc to allocate this message, but some machine layers might have their own memory management for better performance. Like for the Gemini network, when we send a message, we need to register that memory and deregister that memory. If we do this registration and deregistration every time, it causes a lot of overhead. So in terms in LRTS, we implement a pinned memory pool. So instead of using the GNOME alloc and free, we actually use this memory pool alloc. So every time we allocate a big chunk of buffers, and this buffer will be registered once and then be used for multiple times. For the PAMI implementation, we also have the L2 atomic queue for the freeze messages. This is mainly to avoid the mutex overhead. The other important feature charms provide is the persistent message. As we know, most of the messages in charm are unexpected messages, but for some scientific applications, we observed that the communication pattern doesn't change. That means the communication partners and the size of the messages don't change from time step to the other time. And in this case, we can pre-allocate the memory for these messages, and then every time we don't have to allocate and deallocate this memory again. So this persistent message is really good for RDMA support network, because for regular charm message, if we want to implement it on the RDMA network, we have to send a control message first. This is we don't know the receiver side's memory address and memory handler. So, but with this persistent message at the beginning, we register this memory and see the receiver side's memory information. Next time when we call this function, we already know this message. We can directly do a RDMA put. So in order to use this feature, we define the LRTS send persistent message, and the remote side memory information is included in the persistent handler. This data structure can be defined differently at the lower level machine layer. About the collectives, charm provides the common implementation for collectives. Like for broadcast, we have the implementation based on the spanning tree and hypercube. However, if the underlying hardware provides the hardware support for collectives, they can re-implement this LRTS broadcast function to use their own collective function. However, one thing we still need to notice is that all the charm functions are asynchronous function call. If the collective function is blocking or synchronized, we cannot use it. Like in MPI2, all the collectives are synchronized, we cannot directly use it. So what's the status of LRTS work? Now we have LRTS support on all the Korean machines with the Eugenie Gemini network, and including XE, XK, and XC machines. And we really put a lot of effort on implementing and optimizing charm runtime system for various applications. The details can be found in these two papers. And also we have support for the IBM machines, including IBM BlueGen P machine with DCMF communication library, and the new PAMI library for BlueGen Q machine. We also port MPI machine layer to support LRTS, and also infinite band clusters to support LRTS too. So our last goal is about performance. Now, this figure compares the performance of one-way ping-pong latency on BlueJean queue for the two neighbor nodes. This X represents the different charm architectures with and without LRTS support. So the story is that Samir Kumar from IBM started to charm to IBM Q machine, but at that time he declined to use our support, LRTS support. So he has the Hemi original version, and then we implement our LRTS based on his version. And this figure compares the latency. As we can see, for the Hemi LRTS and even also SMP case, we achieved the similar performance. Actually, even in some cases, we even have a little better performance for different message size. This figure shows the bandwidth we achieved on BlueJean queue. Of course, for the small message size, it cannot fully utilize the network bandwidth. Both LRTS and without LRTS support, we achieved the low bandwidth. But when we increase the size of messages, when we use 1 megabytes message, we achieved 3.5 gigabytes per second. That's like 85% of the peak performance. So what about the real application performance? This figure shows the performance of NAMD running APOL1 92K atoms simulation on BlueJean queue. So still we get the same conclusion with the LRTS support. We have similar performance with the traditional charm architecture. So previous is about the BlueJean queue performance. Also, we have the career performance for Blue Waters and Titan. This slides through the performance of 100 million atom simulation. On Blue Water, we achieved the best performance of 80.9 milliseconds. So in this case, it's like every entry method is 1 millisecond or even smaller than that. That's really fine-grained case. And also we scale it to almost the full Blue Water with 25K nodes. Also we scale to the full Titan machine. On BlueJean queue, we also scale up to 16K nodes. So to wrap up, I talk about LRTS charm architecture, LRTS goals, and LRTS interface simplifies the runtime implementation on new hardwares. And on the other side, we maintain the good performance on various machines. So as the future work, as I talked before, when the messages cannot be delivered immediately, we need the machine layer needs to buffer these messages. Actually, this feature is true for a couple of machine layers. We plan to do it in a higher level, so the machine layer should be even simpler. And also, we want to add the fault tolerance interface to detect the fault in the machine layer and be used for our fault tolerance framework. Finally, for the long-term goal, we hope that we can use LRTS implementation for the other runtime system to implement some other program models. That's it. Questions?
So you're using the Eugenie interface now. Have you also looked at the DMAP interface?
Yeah, so at the beginning, we tried to decide. Oh, yeah, the question is, currently we use the Eugenie interface. Have we look at the DMAP interface? At the beginning, we look at both of them, but we found DMAP is more like a shared memory program model. It's more fit for the PGAS language, while Eugenie is used for message passing for MPIs and charm, this kind of message-driven programming models. Yeah.